Hello and welcome. We have now some look into velocity, acceleration and displacement. And let's start with a velocity diagram and see what would be the acceleration and what would be the displacement. We define we have a one-dimensional motion. One-dimensional motion. And for one-dimensional motion, we have the following velocity versus time graph. So velocity v, and on this axis, and on this axis we have the time. So now here we start. This is zero. This is zero, and let's say the velocity has the following property: it goes slowly up. It is constant, and then it goes quickly down. So let's say this point here is 1, and the units is meter per second, and this one is -1 meter per second. Now the velocity goes up, let's say in 2 seconds. Another 2 seconds, so here is 4, and here in 1 second it goes down to this. So and this all is given in seconds. So we have an increase of the velocity, then we have a constant velocity, and then a decrease in velocity. Now assume all of these is a linear increase. So we have v of t for the first part is 0, it starts from 0, and then it increases over 2 seconds to 1 meter per second. So the velocity actually is 0.5. Now I omit the units times t, and t is given in seconds. So this must be a velocity. So 0.5 here means in 1 second it increases to half a meter per second. So the units has to be here meter per second squared. 0.5 meter per second squared times the time is a linear increase of the velocity from 0 to 2 in 2 seconds to 1 meter per second. So this quantity here is the acceleration. Acceleration. Okay, what is the velocity here? This is the first velocity, v1. Here we have velocity 2. Yeah, v2 is not a function of time anymore, but it is just constant. It's 1 meter per second. And then for the last part, v3. Yeah. So v3 is a decreasing velocity, and we start from 1 meter per second. Yeah, so it is 1 meter per second, and then it decreases within 1 second over 2 meter per second squared. So minus 2 meter per second squared, and then we have a t prime. So now you might ask why I write here a t prime. Okay, the t prime comes from the fact that we start here at a position of 4 seconds. So t prime is 4 second minus t. So when t is 4 seconds and t prime is 0. So this one. So now we would like to know the acceleration, and we can do it directly from this graph, but we can also do it a bit more fundamentally. A bit more fundamentally means we know the definition for acceleration. The general definition for acceleration is a change of the velocity per time, dv dt. So we have to make a derivative. So for the first time, if we make a derivative, we get a velocity of 0.5 meters per second squared. That's why I actually wrote here on the top acceleration. So this acceleration is a1 is 0.5 meters per second squared. What is the acceleration for velocity v2? Velocity v2 doesn't change, so therefore a2 has to be 0. And for a3, this is the last part, yeah, what we do is we take a derivative of this one. The derivative of this part is 0, and the derivative of this one is minus 2 meter per second squared. So now we have the acceleration, and if we want to plot for the different parts, and now in the question would be, what is the acceleration a, and the units are meter per second squared, and this is time. So up to 2, and here is 4, and this is 5. So now we have positive, so I put here a line. This is a 0, and what would be the acceleration? Okay. The acceleration initially is 0.5 meters per second. Then, I use a different color. So this is 0.5. This is 0.5 meters per second squared. Then we have 0 acceleration for this time, and for this one time we have minus 2. Okay, just, and then because we want to give numbers to this graph, so this is 0.5, and this is minus 2. So you wonder maybe what happens actually at these points and at these points. What we need to do is we need to know the derivative at these points, and if this is changing abruptly from v1 to v2, then the acceleration is not defined for these 2 points. However, if we have a real motion and we look into these points, then we maybe have a straight line, and then it curves and goes to straight. So there is indeed for any physical motion there is an acceleration defined, and therefore you would expect that we have something like a round curve at these points, something like it would go down here and it would go down here. If it is, if it's not rounded and it is just mathematically defined as a and there's not you can't find a derivative for this one, then you have to omit these points and you can't plot them in the acceleration graph. So this is the acceleration graph. Okay, this is the first part, and in the second part I want to plot the velocity. Okay, now we come to the second part. What is the displacement as a function of time? What is the displacement as a function of time? Now, the displacement as a function of time is defined as the integral over the velocity. Integral velocity dt. We may have to be actually a bit more accurate. This is just a bit a short form. In reality, velocity is a function of, let's say, t prime, and then we integrate over dt prime, and then integrate from 0 to t. So s of t is a function from 0 to t, velocity dt prime dt. So this is our velocity. So what if we look at this first part is 0.5 meters per second squared, and the velocity here is oh sorry, this is wrong. Okay, this is 0.5, so this is how we have defined that one. I was a bit fast. 0.5 meter per second squared times a second. And let's see if the dimensions are correct. Meter per second squared times second gives meter per second, so that's the unit for velocity. Let's do it for S1, and S1 would be then our 0.5. We can write it in front. Then we do the integral, meters per second squared, and then we have to integrate t prime, t prime dt prime from 0 to t. What is that? It's 0.5 meters per second squared, and then this is t prime squared 1/2, and then we have to integrate it from 0 to t. So this is 0.5, this is 1/4 meters per second squared, and t squared. So this tells us that the displacement S, displacement S, goes initially with a power law. And that actually, this is clear, then we know that the displacement is nothing else than the area under this curve. The area under this curve goes quadratically, increases quadratically with time. So that would be the first part. So the second part, S2, just we can use this general definition for velocity, or we use, instead of velocity, we use we know that the velocity is constant, so the displacement has to increase linearly. So S2, and S2 is then nothing else as 1 meter per second times t. Or this is the integration. And S3, this would be V2, this is V3, and S3, this is the displacement of time, is, okay, what we do is we just integrate it, and we know that what already this is integration. 1 meter per second, we start with 1 meter per second, is, okay, 1 meter per second times time, and the other one gives again a 2 meter per second squared, and we already know that this t prime squared gives us 1/2 t prime squared from 0 to t, which is 1 meter per second times time minus 2 divided 1/2 is just 1 meter per second squared t prime squared. Okay, so what we see is that S1 increases quadratically, S2 remains constant, and S3, oh, this is again wrong, this is S3, and S3 is a combination of a quadratic decreasing and a linear increasing. Now, if we want to plot this function in our diagram, so we have then initially, we start with a displacement, a positive displacement, a zero displacement, and it increases quadratically. So it must be a quadratically increasing function. Okay. Quadratically increasing function, what is this value after 2 seconds? We look at it, and this is 1/4 meter per second t squared. T squared, so this is 1 meter per second at this point. Now, what is happening for the displacement afterwards? It increases with 1 meter per second times time, plus, so we start from this position, and then it increases linearly with 1 meter per second. Okay,